let us start. So today's topic is the strain and displacement relations. So recall that we have discussed up to stress transformation, and then these two topics, true stress and stress function, these two we have not discussed up right now, because afterwards when we will go into details of strain analysis, then the true stress and this true strain, these two will be discussed together, okay, as well as this stress function, the concept of stress function we will discuss in connection with strain compatibility. So these two topics will be discussed after some 2-3 lectures, you can say. Okay, let us start. Now if you click here, you will go into this slide, but here what we did is we have downloaded this slide, so I am showing it from my laptop. Okay, so this is today's topic, analysis of strain. So what are the subtopics that we will discuss? These are written here. What are the types of strain, how we measure them, strain measurement part. Then the strain displacement relationships we will be discussing. Now with these types of strains, this is important aspect. We will also discuss about the change in direction. Then gradually we will come to this state of strain at a point. So this is similar to our earlier idea of state of stress at a point. So that means we determine the strain field. So again, in that connection, in connection with stress field, we determine principal stresses. So here also, in connection with strain field, we will come into the idea of principal strains, and strain invariants, they will also come. Then principal directions, they will also come. Some compatibility condition and stress function, these two we will discuss together. And then the reverse relationship, this displacement field from strain field, okay, this we will discuss afterwards. Actually you can say this is something like determining stress function from a stress field. An equivalent thing is this thing, determination of displacement field from stress field or from strain field. Okay. And finally, in connection with our analysis of stress, we determined an equation of equilibrium. So that equation will again describe through displacement field, and those are known as displacement equation of equilibrium. This is the topics in our analysis of strain. Right now you see some complication comes in connection with the strain measurement. What is this? There are various strain measures. Okay. So the idea is there in our stress measure also, there are various measures of stress which we didn't discuss up to this point. When we will go into true stress, okay, there you will see that there are different measures of stress at work. So then these questions come. Actually for stress field also this question is relevant. Of all the definitions of stress and strain, say which one is the best? Now the answer is there is no one which is more correct or less correct. So everything depends on the particular application for which the stress field and strain field are being discussed, are being used. We will see to that. Okay, some are just more convenient than others for a given application. This is the thing. Now you know different types of strains. Let us elaborate on that. Okay, these are types of strains. We will come to it. But then you see what is the genesis of strain. This is gradient of the displacement field. So today's topic is strain displacement relationship. Right. Now this displacement again is not a unique thing. Actually, this displacement consists of two parts, this displacement and deformation. When we say displacement in general, we mean both these things, displacement and deformation combined. So this is true when we say the term deformation. Okay, these are some loose terms, simply standalone way displacement or standalone way deformation. So in totality there is two such things, displacement and deformation. We will go into that. So what is written here? These are the heart of continuum mechanics, and the deformation gradient is the center of the heart. So what is deformation gradient? This is the strain. That you know, strain is the derivative of displacement field. du dx is your epsilon x. Is determined. Okay. Now the deformation gradient is used to separate rigid body translation and rotation. So there can be a rigid body translation, there can be a rigid body rotation from deformation. So now let us come back to this. There was displacement and deformation. So what does it imply? It is term displacement. This displacement refers to this rigid body translation and rigid body rotation. The other part is the deformation. So the complete picture is revealed when we isolate this displacement, and in displacement there is this two part, rigid body translation, rigid body rotation. In addition, there is a deformation. This is the complete. And a gradient of displacement field is applied to analyze the situations, rigid body translation, rotation, combined deformation, rotation, etc., etc. In general, in your undergraduate studies, you have used this displacement field in 1D and in 2D, right? Up to 2D you have analyzed, right? So the same thing, if we extend in 3D, we will have three such components, and this is the general description of U. So at any direction n, there are three components, which are this U along I, this is V, this is along Y or J, I is say along X. So U is the measure along X direction. So this is some numerical value, measure of strain along direction I or direction X. And you understand U, V, W, they are components along this IJK direction. That part is clear, but note this value of U, okay, the vector quantity, its value is different at different points of the body. Okay. So that gives us the displacement field. This displacement field contains some field along X direction, a field along Y direction, another field along Z direction. So what is important to be noted here is that this U, V and W, they are also fields. Is it clear? Actually, for each and every point we have different value of U. So we have different values of this U, V and W. So if we collect the values for U separately, for V separately, for W separately, what we get is basically a field for u. That is clear, right? So this idea is useful. Afterwards, we will see that the derivatives of this u, v and w, they exist along x, y and z dimension. So if these are fields, then that is obvious. Okay, that part is clear. Now then, okay, this part we have discussed, and then you see there is another distinction here. Okay, that is given by this relation between strain and displacement. We will come to it after. Before that, you see strain represent change in line. This change means change in the measure of material lines, in the measure of material angles, and in the measure of material volumes. This is the thing. So this quantity strain that might be coming from a small displacement and a small rotation. Okay, in that case, what we get is a linear relationship between strain and displacement. The strain is gradient of the displacement field. Okay, so this relation, like epsilon x is 1 by E into, no, I am sorry, this epsilon x is du into dx. Okay. This thing is going to change for this type of strain field, and particularly if we have in the field of u a second degree variation in u. Understand? Then a simple linear relationship between strain and displacement will not be needed. Okay. So for small displacement, and this can be small rotation also. In general, the displacement and deformation, they gives the complete behavior of the body deformation or body displacement. These are two components. Now, we can classify them in these four categories. There is small displacement and large displacement. Similarly, there can be small rotation and large rotation. Okay. And you understand these four subcategories will come from there. If the combination is small, it is linear analysis. Okay. If we have large rotation, what we get, this is called a geometric nonlinearity. Okay, that means as such there is no material nonlinearity, or we can say the material remains within elastic limit, say. Okay. Only, as I was telling, the relationship between strain and displacement, they are not remaining linear. Okay. Now for large displacement, what will happen? We will get this material nonlinearity. This, okay, one thing is material nonlinearity we will get, that is not mentioned here, whatever. Rather, if displacement is large, okay, in such case, this measure, there are various measures of strain, it is measured written here. The usual measure of strain that we use in our undergraduate studies, that means strain is given by the change in length divided by the original length. So that definition is not exactly the only definition. There might be some other definitions in between which can capture the deformation process in a better way. So this is a particular way of expressing the deformation. There are other definitions also. So in such situation, other measures of strain, they come up. Okay, with large rotation, we have this description updated Lagrangian as well as this geometric nonlinearity. This will come, and in addition, there is another complexity which comes from material nonlinearity, which we will be discussing next when we will be discussing the relationship between stress and strain. Okay, then only the material properties will come. So this much is fine. Now the types of strain and measurement. So these measurement techniques are different types of measurement techniques are there, and that we will be discussing afterwards. So these are the types of strain which we use ordinarily. So for plane strain, we are familiar with normal strain and shear strain. So the pictorial representation of this plane strain and this shear strain is shown here. A three-dimensional body deforms, and if we take a view in a plane, there can be extension in x direction as well as there can be extension along y direction. So this extension, we say this is epsilon, and this is given by this increment, okay, in displacement du for this elemental length dx. So our epsilon x becomes du dx in small strain and in 2D. That part is clear. Epsilon y you also understand. And how we measure shear strain? Shear strain is measured with reference to an original 90 degree. Okay. So you see here, or how this shear, you can identify the shear in this pictorial representation. If we take a view from here, this is what we get, right? So this is sheared. Okay. The rectangle has taken this particular shape, like it, or some sort of deformation is there. Now what we do from this measurement, what we get is basically the change in this particular angle between OX and OY, right? So this original 90 degree between these two coordinate axes, that is now rotated as if by angle theta. Okay. And then what we do, we take tan of this theta and we say that actually rather this is, if this is delta x, then this tan of theta, this theta is your delta x by this y. Right? That is one part. And then what happens? So in addition, this is a case where we have deformation along x only, and in such a case, in addition, if we have some deformation along y, okay, then there would be another displacement of this particular point as shown here. This point A has displaced, this point B, it will also displace. So we'll again get some angle here, some rotation of this line. So in totality, this angle between OA and OB, these two other directions, OX and OY, this is given by these two angles, this theta yx, and here we have theta xy. So and tan of that theta x and theta y is given by the measure. Here we will have a delta y, and this is our dx. Okay, we will measure that. So from there we take tan inverse of, that means that angle is gamma xy. Now in totality this gamma xy and gamma yx, so this one is gamma yx, this one is gamma xy. In totality this is gamma xy. So this gamma is our shear strain, but it contains two components that you understand. So when we will go into mathematical description, that means we will go into the description of strain field, we will see that instead of this gamma xy, which is our shear strain, in general that is what we use in our Morse circle in our 2D stress analysis or 2D strain analysis. That consists of two parts. And this thing, this gamma xy by 2 or say gamma yx by 2, they are represented as epsilon xy and epsilon yx. So here also the notation is identical with our stress notation. So this epsilon x will be denoted by epsilon xx, this is epsilon yy, and now we have epsilon xy and epsilon yx, right. So this 2D strain field consists of 4 quantities. We can represent them by a matrix, 2 by 2 matrix, and that is clear. Okay. How this is measured, that is also clear. For a 3D body, what we have to do is we have to take a line along some direction, along direction n, and we have to see what is the change in the length and direction of that line. This is what we will do. Let us progress. And this is the measure I was talking about this. Okay. So how totality this gamma xy is a measure of this angle theta 1 and say this angle is theta 2. And as you know, for very small angle theta, tan theta is equal to theta. That approximation is made here, and that is why we have classified previously the problem as a small rotation and large rotation. Okay. For large rotation and associated with large displacement, this assumption will not remain. Okay. In that case, we cannot use such a relation. Whatever. So that you understand how it is coming like this. This theta 1 is equal to tan theta 1 and tan theta 1 is del uy by del x. Okay. Theta 1 plus theta 2 is our gamma xy in totality, but afterwards we may represent this as half of gamma xy plus half of gamma yx as well. So strain represents change in material lines. That change in measure of material lines means this length, it will give normal strain, the angle which will give this shear strain, as well as there would be a volumetric change. Here you can understand there is a volumetric change as well. So that will also give rise to a strain that we say is a volumetric strain. Now of course you should note that this volumetric strain, it comes from this deformation field only. Okay, and this displacement which comes from a rigid body translation and a rigid body rotation, that won't change the volume. Only deformation part will give the volume change. Okay, this part is clear, change in right angle, and this is also clear. By definition, the shear strain is positive when the angle is reduced. Also, we have not represented another type of phenomena. It will come. Okay. Now, what is the genesis of strain? They are primarily due to stress. Stress causes strain, as well as there might be a temperature change, which will also generate strain. This thing we have somewhat discussed earlier, which is primary stress or strain in the atomic level, how stress and strain are generated there. Okay. There are some other contributions to strain field. Those are, say, this is moisture content, and some other sort of phenomena are also there. Those are the reasons for strain. And here the idea of displacement and deformation, this is shown here somehow. Okay. So here you see this is the initial body, and these are the body represented after deformation. So these two phenomena are designated by this time 0 and time t. In general, in our solid mechanics discussion, we do not discuss this effect of time in the process of deformation. Like this is our body at initial position before applying force or something, whatever, temperature, field, whatever. And if this is the final position, the contribution of our the elapsed time in the process, that part we neglect. When we take this time interval in consideration, we get those phenomena like creep, other things, okay. In between the rheology that we had discussed earlier in our classification of the solid mechanics part, these phenomena will come anyway. We are not taking the effect of time or time duration between this deformation. So we are as if taking that this is an instantaneous thing. So what is shown here is a rigid body rotation. So you understand, this is what we can rotate this thing at this point, and there is a translation also. This is rotated here about this point, okay, go on there. This is a elongation part only. Okay. This is elongated like this, like this. It is elongated and then it is moved there. And if we combine these two, this is elongated as well as there is a rotation. We will get this configuration. Now, in general, so this is our body. Right? Initial configuration, and then we are getting this configuration after application of that, say, the pressure, stress, temperature change, whatever the reasons which causes strain. Right? So that is what is happening here. So here what in describing the deformation and strain, we need to define this configuration, initial configuration. This is known as undeformed configuration. And then this deformed configuration, this also need to be defined after deformation, time 1 means after deformation. So this is known as initial configuration, or this is reference configuration. This initial configuration is also reference configuration. Why it is like that? We will see. I will explain now why it is like that. And this is known as current configuration. Now this is another terminology is the material configuration. This is the spatial configuration. Now whether we are tracking a point, okay, as a material point or as a space point, that also makes a difference in our strain measure. Like there are different ways of measuring strain actually. So these things are important. So that part we will be discussing in a different lecture. Okay, we'll address it afterwards. So now the point is why this is also called a reference configuration. That is needed when we use this idea of updated Lagrange. There can be various other ways of describing this large displacement phenomena. So as updated Lagrangian is written here, this means the total deformation process, say from time 0 to time n. The total deformation process is decomposed into n part. Okay. T0 to T1, T1 to T2. That way, if we progress, then starting from this configuration, we come to the second configuration. This is at time T1, and then we take this as the reference configuration, and then we go into the next step, time T2. This is clear? So this is the reference configuration or initial configuration. This is here, and along with this, different measures of strain it comes. You see. So that part, I will be discussing only one particular example here. Say from this configuration we are getting this one. Okay, this is the final configuration. Now you see this particular configuration, okay, described by the coordinates x. Okay. These coordinates are functions of this particular coordinate. That means we have to start from time 0 and then we will come to time 1. We cannot go into time T2 directly.
Yes.
So you understand this idea, why it is like that. And for reference configuration, this position, the functions of this x1, x2, x3, this is our initial coordinate system, which represents the initial configuration. And what is there? So how we get a point, particular point which has moved from this location to that location. Say this is given by this displacement field u. So this you understand, that means from this point to that point the displacement is u. Okay. Now description at time 0, say that is our capital X system, and here this is our small x. So the difference between these two vectors, x minus small lowercase x minus capital X, that is the same, that you know,
Yes.
our idea of vectors, and this can be written also in this form. And this description of our u field, okay, is there. If it is there, and if we take a gradient of that, that is gives us the strain field, right? And say that is the f here. F is the derivative of each component of deformed x vector with respect to each component of the reference capital X vector. That we have already seen previously. Say here also, if we have a displacement field like this, then we have strain which are coming from the derivative of this u along x, y and z. They will give a normal strain
Yes.
along x, and the other two derivatives they will give the shear
Yes.
strain u x y and u x z. That is clear. So that is what we will be getting, and this is our the derivative matrix as the same thing. And so what will happen if we take this derivative with respect to this initial configuration or reference configuration, then this is the derivative del f with respect to initial configuration capital X is 1 plus something, or we say this is our identity matrix plus this del u del x. So this is one way of representing it. Reference to this configuration we are describing. But you see what is shown here is basically the same phenomena can be described with respect to this configuration also. Okay. You take this example. Say I have an initial body like this. It is a 2D body. Understand that this initial body has 4 corner points 0 0. This is 1 1. This is 1 0. This is 0 1. And this blue rectangle, it indicates the deformed configuration. And in general, the deformation of any point is given by this matrix representation. So if you take a derivative of this, you will get this gradient matrix, right? Is it clear? 1.3 minus 0.375. Yes. This is what we will get. Now you see this particular matrix F, this we can represent through a rotation matrix. This R, what is this R? Actually say this is our R matrix. Okay. So let us, we can define this R like this. This is the thing. You can use your MatLab also to evaluate this thing, or by hand calculation also you can calculate. Say this much is our rotation matrix, and that is post multiplied by another matrix U, and here this is pre multiplied by another matrix V. Okay. So if we use this particular rotation matrix, now is it clear that this is a rotation only? You see here, this is a case of rotation only, and this is a case of pure translation, right?
Yes.
In pure translation, this is the representation,
Yes.
and the corresponding derivative part, it would be only 1 1, this would be 0 0, is it not? 1, then there would be some 0, or no, this is for translation
1 0 0.
1 0 0 1. Okay. This is for rotation. This is what we will get. This is the relation here. So if this part is equal, this is sine theta and minus sine theta. This is the say rotation matrix here. You see here, see, this is the same values. This is 0.5 minus 0.5. Okay, so this indicates as if this is a rotation matrix. Okay, and this is post multiplied, this is pre multiplied by this. This multiplication you can carry out in MatLab very easy. Define these two matrices, and this multiplication will give you this value. Okay, this is what we are getting. Same thing almost. Okay. So this U is right stretch tensor as it is known, and V is left stretch tensor. This is true for 3D strain field as well, displacement strain field. So what does it signify basically? As if we can describe this thing with respect to this, as well as we can describe this one with respect to this. Okay, that part is possible. So these things will discuss afterwards when we will go into other measures. Some are known as Lagrangian, etc., etc. These are there. Okay, the strain measures. Actually, you see this is some of the definition of strain, okay, which we use for large rotation, large displacement, etc. And what happens when both are small, when we are taking a linear relation between strain and displacement? These quantities, they are these individual components. That means here, this one individually, they are much less than 1. So if that is the case, then their multiplication, say between these two terms, much less than 1, much less than 1, and it is too much less than 1. It will happen. 0.1 into 0.1 is 0.01. It will happen. So we can neglect that. This is a particular measure. This is known as green strain. This is Alban's strain. Actually, this is the rotation part. Okay, that something rotation is associated with that. And so, neglecting this part, what we get is the same measure here. Okay. So, the quadratic term, or this is neglected. So, what we get, this one, keeping only linear term, what we get is called Cauchy's strain tensor. It is named similar to our Cauchy's stress tensor also. That's the thing. Now, this is what we will be using right now. Although this is what we will be using in our 2D analysis. This is what for today's lecture we are using this particular measure. Okay, in 3D analysis, there we will go into the green strain, measurement of green strain. So today we will be discussing up to this point only. And the next lecture will be a discussion on green strain that we will carry out for 3D displacement. Okay, what else? There are two more ideas associated with that. One is uniqueness theorem. What is that actually? With this, some more idea is also related. One is this. See, we have talked about continuum mechanics, right? Whatever we are discussing is within the domain of continuum mechanics. So here we have this particular idea. The material point forming a closed curve at any instant will always form a closed curve at any subsequent time. Say, for example, if we consider this is initial configuration, or at time 0 this is configuration, and we have a circle around this point. At this point we construct a circle. Then at a subsequent time interval, this circle can be an ellipse. Okay, but this closed curve has to remain a closed curve. It cannot open up. This is the idea. Form a closed curve. The material points forming a closed curve at any instant will always form a closed surface. And matter within the closed surface will always remain within. Okay. So what does it mean? The material points which are enclosed within this circle, somehow they have to remain within this deformed elliptical shape. Understand? So that means a point outside of this circle here, it cannot come here within this body. Okay, that part is clear. So material confined within this circle has to remain within the deformed curve which is now defining that particular circle. Okay. So these are the two ideas to maintain the continuum mechanics phenomena. Some other thing is, one is this uniqueness theorem. If two displacement field u and u prime, they represent same strain field. Okay. Then this a third displacement field, say, which is given by this u prime and another displacement field w, okay, which is a rigid displacement field, that is also a valid displacement field, from which we will get back the same straight field. So we can say these two, u and u prime, they are related like this. So which means these strain measures, what they measure is basically the deformation part. Okay. The body displacement part, the rigid body displacement part, okay, this rigid body displacement part, that will not come in this deformation gradient matrix. Okay. This we will discuss further in connection with obtaining displacement field from strain field. That poses a problem there. That is one. Another is a compatibility theorem. The strain field epsilon correspond to a, you know what is a C2 continuous displacement field. That means it maintains the continuity up to second order. C0 continuity is the value continuity. C1 continuity is your slope continuity. And C2 is your curvature continuity. So for this body, if we consider the strain field, that strain field has to be somewhat and be described by a second order function at least, so that up to C2 continuity is maintained, corresponds to a C2 continuous displacement field. And they satisfy the compatibility equation. You know, this is a vector calculus notation, grad vector, right?
Yes.
What does it indicate? Rotation or something? What? I am not accustomed with vector calculus much.
So this is the characteristic equation of the vector calculus.
No, actually this is a measure of something, sun or whatever, I am not very sure, but this is the mathematical description. It has a corresponding physical significance as well. Okay. Might be. I will check, let you know afterwards. Okay, so these are some conditions for our discussion of continuum mechanics, within continuum mechanics domain. Now this is what is the general description. So how we measure? We measure basically a line element, change in length of the line element. This is a phenomena in 2D, right? And in addition, we will measure change in the right angle between two reference lines. So here our point of interest is here at a local point, say P at position P0, that means at time 0, configuration Q0. So perpendicular to this P0 Q0 line, there is another line P0 R0. The angle between them is 90 degree. This is deformed configuration. Okay, so as if this point P is now displaced at this point from P0 to P. We won't say this as P1, say this is our current configuration, as if Then the change in length of this line element is 0. This has become our changed length S. Okay. So we have to take a differential element of this line here at this point. We will take a derivative of that. And how we will measure shear strain for this line P0 R0. Again we have to track that line here. So this is the line PR, this is PQ, and at that point we will construct tangent to PQ and PR. This is clear?
Yes.
So again, say on this tangent line, let us construct a perpendicular. Is clear?
Yes.
So with this line, this is the perpendicular shown by this perpendicular, and now this is our shear strain gamma. Understand? Okay. This is the measure of longitudinal strain or normal strain. This is how we measure the shear strain. Let us focus on that, what happens there. So this particular point is within a body. This is our point, reference point. Then at each point of the body there is some displacement. This is the general displacement field. So this is what we have already mentioned. This U, V, W, they are individually a field. So the components U, V, their partial derivative, that also exist. Okay. So U varies along X, Y and Z. That is there. And what we are doing here, say, we are discussing in 2D, say in X, Y plane. I can do it right. So in XY plane, if we form a small rectangle there, okay, we project it in 2D. This is what we will see.
Yes.
So this is the side of the rectangle delta X and delta Y. And at this point O, here we have some reference coordinate frame. From there we can locate point O, where our displacement field is given by this. If this is in 2D, what we have, this is Ux plus Vy, that's all, or X cap, Ui plus Vj. So what is deformed position of point O? This is the deformed position, right? Shown by dotted line. The same thing, reference position and deformed position. So this is reference position, this is deformed position, this point has gone there. This point has gone there. Okay.
Yes.
What is the measure? Say, if this point is say 0, 0, right? Where we can neglect this X and Y coordinate of point O, so let us shift the origin at this point. So in that case now, this O prime, this has coordinate U and V. Okay, the displacement field at point O. What is displaced position of point D? In initial configuration, its definition, its coordinate is delta X and delta Y. So this D is going into the deformed configuration D prime. At point D, the displacement field is not U and V. What is displacement field of D there? Okay. This is U and variation of U along X, del U del X into delta X, right? Then of this point D, what is displacement there? If we consider this point here itself with coordinate delta y, then we have this V plus variation of V along y, delta V delta y with delta y. This is clear. And in addition, this point D is at a distance of delta y in this direction. So the u variable, the value of u at point C is not identical at point D.
Yes.
Because that u is a field variable. So what is that variation? That variation is this delta u delta y into this dy. For this point D, okay, that variation is this delta u delta y into this delta y. And again at point D, there is a component. This is this delta v into delta x into this say dx or delta x on say. So that is how we will get the coordinate point D prime. So like this, our u is the complete displacement and v is the total displacement. We will come to it. So this is how we are getting coordinate of point D prime. Similarly, for point C, it is going to C prime. Okay, this coordinate along y is a derivative of v with respect. This is C is along x, so v plus del v del x into delta x. And for point E, this is delta v delta y into delta y. E is going to E prime. So that way we can find out what are the coordinates of these points. And in general, what we will do, we will find out the position of point or coordinates of point O, D, O prime, D prime. And we will find out the line element OD and its displacement position O prime, D prime. What it will give us? The change in length of the line element OD as well as the change in angle for the orientation of the line OD. Is clear? So that will give us the principal strain or normal strain and shear strain. That is what we are going to do. So here this is shown here in general for a general deformation. It is not that there is a pure rotation or pure shear, right? So previously we have discussed about translation, rigid body translation and normal strain. They can be mixed up. Similarly, the pure rotation and shear, they can also get mixed up as shown. So this gives the net shear strain value. This gives the net normal strain value. So these expressions will come. And what is shown here is for 3D, what is the meaning of that? The variation of delta u, delta x, delta del u, del x, del u, del y, del u, del z. Okay. For a 3D field, this is what is meant by that. Okay. This del u, del x means this. we are getting u field, measure of u field at x plus dx, y and z coordinate remains same. Okay. So this is along x, this is del u del x. What would be our del u del y? So here we have to change the y coordinate. This has become y plus dy. X and z coordinate remains same. So this is our del u. Okay, this part is clear, and these are shear strain definition, and this is the rotation part. This is what we have already discussed. What is gamma xy by 2 is epsilon xy. This will come afterwards. Okay, now this is the displacement field or deformed position is given here. So what we note from here is that to obtain this deformed position, actually this is the deformation of the body. That means if you, from this figure, understand at this point our displacement fields are v1, v2 along xy. Here this is v3, v4 along xy. So this is ultimately the deformation of this line, and to measure the strain we need to shift this particular line at this point, and then we have to orient along this, and then we get this is the quantity which is coming. That would be divided by the initial length L, we will get the strain from there. This is clear. So that is what is basically another operation which is there. So as if this is not straightway the derivative of the displacement field. When there are two lines, one is this line, other one is this line. From analysis of the displacement field, what we get is the length of this line and length of this line, but the reference point has moved. So to measure the change in length, what we need to do, we have to shift back this point O prime into this reference point O, and then we have to align it. Then only we can find out what is the extension of the line to obtain our normal strain. Okay, and if we shift it parallelly, that means shift point O prime at O through a parallel translation of line O prime D prime, then the angle between OD and O prime D prime, that will give us shear strain. So that is what we are going to discuss now. Okay. So let us take example of this figure, as if this is now re-represented by this line PQ. Okay. The distance of point Q is dx and dy along x and y. Point P deformed to P prime, Q deformed to Q prime. Okay. So what is displacement of point Q? At point P, this is u and v. So P prime is x plus u, y plus v. What about this point Q prime? Point Q is x plus dx, y plus d. This is initial configuration. So for Q prime, it is not only u plus v. In addition, we have these two terms. Clear? This is what we have discussed earlier, and this is position. Now we are shifting this point. P prime is going into P. This is the thing, right? This is the figure. This is translated back at P. P prime has gone to P, and this is a parallel shifting. If this is parallel shifting, then the angle between PQ and P prime Q prime, it is coming as this psi, angle psi, say. Okay. And this particular angle psi is a function of initial configuration of this line PQ. That is given by this angle theta. Right? We could have selected another line PQ at a different half of this theta, 2/3 of this theta. Anything was possible. So this psi, this is a function of this angle theta, so psi suffix theta. And similarly, this is also true for the normal strain. If we would have taken a different angle theta, the extension of line PQ would be a bit different. So whatever extension we are getting on this line, that is represented by epsilon suffix theta, this epsilon theta. What does it mean? These expressions which we are going to derive, this is valid for this particular orientation PQ at an angle theta. Okay, this is clear. Now let us find out how much or how to obtain point Q double prime from Q. What is Q double prime? This is the position of point Q prime when we have translated P prime Q prime parallelly to point P. Okay. So quite obviously from point Q along x we move by distance r, qr. That means we have drawn a horizontal line from Q, and from Q double prime we have drawn a vertical line. They meet at this point r. So qr is distance along x, r, q double prime is distance along y. In addition, we have dropped a perpendicular from Q on this line P Q double prime. Actually, this point P is a triple point. This is point P, this is point P prime, as well as this is point P double prime. So from point Q, the perpendicular on line P double Q prime, okay, that is S, foot of the perpendicular is S. QS is perpendicular on P Q double prime. Okay, that part is, this is our construction. What is QR? This is only this much.
Yes.
Yeah. Because this U and V, they are translated back. This U and V, that is translated back. So from coordinate of point Q prime, this U and V part is now neglected. We are getting this as QR, and this would be R Q double prime is this part only. Okay. Now from here, if these two are known, we can find out this QS and SQ double prime with reference to these two lengths, these two lines, is it not? Okay. SQ double prime is QR cos theta along this, and as this angle is small, we are taking this is QR cos theta plus R Q double prime. So if this angle is also theta, this is another cos theta. Now what is this? This is QR cos theta, QR cos theta, and it would be QR. We are dropping a perpendicular here, say if that angle is theta, which one is angle theta now? This angle is becoming theta, right? Or yeah, this angle is becoming theta. So this is our sine of theta. Is it clear? From R, let us drop another perpendicular here. So what is the angle between R Q double prime and this one?
Theta, yes sir.
That is theta. So this perpendicular is cos theta component.
Yes.
And along this we have sin theta component. So this is sin theta. And here for measuring QS, we are getting the component of RQ prime along this. This is our cos theta component. Clear? And minus of this QR, this is producing a component outside of that we have to deduct it. Contribution from QR
Yes, yes sir.
in this particular direction. So this is minus. Okay, this is very fine, quite clear. What is extension now? Is it extension? Actually we have dropped a perpendicular, right?
Yes.
And you see, if this particular angle is very small, then cos of this angle is almost 1.
Yes sir.
So this PS is basically PQ cos of this psi theta, which we can take as if equal to 1. So this PS and PQ, they are almost equal. This is our original length. This PQ is our original length. And you know that here, this is an elemental shape. This is dx, this is dy. So line PQ has a length ds. Okay. So what is elongation here? SQ divided by PS, right? This is elongation SQ double prime, and this PS is original length. So that is our epsilon theta, is it not? Normal strain epsilon for this particular angle theta, epsilon theta. So this is SQ double prime. Where is our SQ double prime? This is SQ double prime. Divided by PS, that means divided by PQ. Clear? What is QR by PQ? Actually, the thing is QR is given by this.
dx is a QR equal dx.
Okay, this is QR. This is QR. When we divide this by ds, that means by PQ, what we are getting? We are getting this del u del x
dx by ds.
into dx by ds. Here, from here we are getting del u del y dy by ds. This is the cos theta, this is the cos theta. And other part is in SQ double prime, we have QR cos theta plus RQ double prime sin theta. This RQ double prime, the sin theta is here. So RQ double prime by PQ, that means dP dx into dx by ds. This much is clear.
Yes sir.
Now what? What is dx by ds? If this is ds, dx is ds cos theta. So dx by ds is cos theta. Clear? This is our cos square theta into del u del x. What is this? dy by ds, dy by ds sin theta. So this term is sin theta into cos theta del u del y. Del u del y sin theta cos theta. From here, what we will get? We will get a cos theta. dy by ds is cos theta. So sin theta cos theta del phi del y. del p del q.
dx by ds sin theta.
And from here, this is what we are getting. So this is the general expression epsilon theta. Okay.
Yes.
Now here what we know, the maximum value will occur when gamma xy is 0. That we get from the physical reasoning, that corresponding to maximum shear strain, maximum normal strain, shear strain is 0. That we can find out, or other way, we can also find out what is the maximum value of this gamma xy. What is this gamma xy? It is a measure of this angle psi of theta, right?
Yes.
Now, it is not directly a measure of psi of theta. What we have to measure is what is the change of the angle between line PQ and a line, say PT, PQ and another line PT, which was perpendicular in its original configuration. Clear? What is the angle of this line PT? This reference angle theta is now pi by 2 plus theta.
Yes.
Now, if this is the general expression for epsilon theta, then what will happen for the expression at theta plus pi by 2? We have to substitute this theta by theta plus pi by 2. This part is clear. So before going into shear strain, we observe that in general shear strain is given by this gamma theta, right? Or this angle gamma theta is
Sin theta.
tan of this is qs by ps or qs by pq, because ps is equal to pq almost. So that is a tan theta actually. So if we substitute that, what is qs? This is qs, right? That divided by pq. So this will give us gamma or psi of theta, right? Psi of theta, this is what we are getting from where?
This QS
From here, right?
Yes.
This part is clear, minus this cos. So check this thing, you have to take the slide actually and find out this is the thing. And we observe that this is theta plus pi by 2, okay. So there cos of this angle is minus sin theta and sine of theta plus pi by 2 is cos theta. So this is general expression for that angle psi theta. So that angle at theta plus pi by 2 will be like this. Cos theta is minus sin theta, square is again sin square theta. Okay, here sin theta is cos theta is minus of sin theta, so this plus is becoming minus. And here again, this sin square theta will become cos theta. Minus remains minus. This is it. So shear strain is the change in angle. So this minus this is our gamma xy, or say gamma theta, right? So find out what is happening from here. Cos square theta minus sin square theta. Actually, this is what you will get from these two. Is it okay? How many terms with sin square theta we are having? Sin square theta, del v del x, plus del u del y.
Minus minus plus y. This equation and equation will be subtract, then this minus
Okay.
will be plus. Okay, sir.
Right? Is it okay?
Yeah.
Oh, actually we are subtracting, right? So this plus and minus, this minus is getting again positive. So we are getting twice of sin theta cos theta.
So this equation and this minus this, or this minus this.
What is written here? Gamma psi theta this minus this.
Initial minus final.
Whatever. So this minus will become plus. We are getting plus here. Okay. And this is what will come.
Yes, sir, yes,
You
sir.
check it. Is it coming?
Yes, sir.
Okay, fine. So this is the expression, and then this quantity del v del x plus del u del y. This is our this shear strain gamma xy, right? And actually this quantity del v del y and del u del x, this is epsilon x and this is epsilon y. Okay, this is what we are getting as gamma theta. Actually what is represented here is half gamma theta. You can say gamma theta is multiplied by 2, it would be gamma xy, and here we will get it. Whatever it is. But the thing is, for principal strain direction, the shear strain is 0.
Yes.
So we have to take a derivative of this with respect to theta. Do it and make the derivative of this with respect to theta equal to 0. This is what you get. So this is so if here we put this gamma xy as this,
This is cos 2 theta, this value.
okay, that is what you have to carry out. It is for your part, but this will come.
Yes.
Okay. So this part is okay. So this is how we have analyzed the problem. But what we did in the process is basically a shifting of this line.
Yes.
That part we can do here, but we need to devise a rule to carry out this operation. So here, take a note that instead of finding the strain through this process, if we calculate the square of this quantity and square of this quantity, that means p prime q prime square minus pq square, and then we subtract, what we get? pq prime squared minus pq squared.
SQ square.
A square minus b square is a plus b into a minus b, right?
Yes.
So there we will get pq prime minus pq, that is extension of p,
Yes.
into this pq plus this pq prime. And this pq prime is pq plus epsilon into pq. This change length, so this is pq plus epsilon into that pq.
Yes.
So that is the idea we will be using next. Actually this is the idea for finding out the green strain. Actually if we use that particular concept, what we get is green strain. Okay. So now we have to keep these components. So you understand that shifting this particular line there, what we did here manually, that is not possible through a mathematical generalization, right? So instead of doing this thing, what we will calculate here is this green strain. So that is what we are going to do in 3D strain analysis. Is clear?
Yes.
this is what we are going to discuss in the next class, but idea remains same. In 3D XYZ coordinate we will consider a line OP say, and we will consider another point Q somewhere, okay, in this 3D plane, and we will consider displacement of line PQ to position P prime Q prime. This displacement field, and then we will calculate the grid state, because here it is not possible to shift everything at this point, that way it is not possible, rather we calculate grid state. So this is where we are stopping today. Next day we will start from here. Okay, so let us stop here.